Today I'd like to spend a little bit of time going back through the transition between different formats, polar versus rectangular, for these equations. And by no means are we going to target every single possible type of equation that we can see. Basically what we're going to do here is deal with lines and circles, okay? But hopefully that then is an introduction that allows us to realize or recognize the way or the structure in which other types of polar graphs are created, okay? Which we'll kind of introduce towards the end of the period today. This is these other equations. When I was in high school, we did the same thing. Didn't spend a whole lot of time on the changing from one equation to the next, okay, a polar equation to a rectangular or vice versa. We might have done it. I don't recall ever doing it in undergrad work in college. But when I got to graduate classes, the course called complex analysis, okay, which is really understanding what the complex plane is and all the things that you can do with the complex plane, was heavily based using this type of manipulation, okay. Basically, in the complex plane, what we like to do is convert things from rectangular to polar so that we can graph and do other types of algebra much more efficiently, okay. So that's maybe give you a heads up on where you're going to see this again. And the answer to that for most of us is probably never again, okay. But I think it demonstrates a little bit of interest. Maybe it demonstrates maybe some technology components that this math is used in, okay. And maybe we'll talk about that as we get through a couple of these. But what they are, they're just like any other equation. If you have an equation in rectangular form that has y equals mx plus b, then it is always a line, right? I can change the m and the b, but I still get a line every single time, okay? So on Friday the other day, we took a linear equation that was in rectangular form, so this one here. And we went through a process that gave us a polar equation right there, okay? Both of them produce the exact same line. This one is based off of inputs being x and outputs being y. This one's being based on inputs being theta and outputs being r, okay, or the radius. They produce the exact same image, okay? Now, when I change this 3, and I change this 1, and I change this 6, nothing structurally should change. I should still go through the exact same kind of protocol for converting that new rectangular equation into its polar counterpart. So on Friday, we realized, or we made the connection, that x is always equal to r cosine theta, and y is always equal to r sine of theta, and then r squared was x squared plus y squared. So we're going to use those relationships to merge, or not merge, but change a rectangular equation into a polar one. So this linear one is I think the easiest. I don't want to say the easiest. I think the circular ones, when we start in polar and go to rectangular, those are by far the easiest. But this is not too bad. You simply take this x and you're going to replace it with that thing right there, r cosine theta. So I get 3 r cosine theta. Plus then this y, which I'm going to replace then with that thing there, r sine theta, and it equals 7. And that is a direct substitution, and we now have our polar equation. Now, much like this equation here, this in rectangular form, it's fine that way. But if I asked you to graph it by using maybe a table, you'd have to choose x and maybe say, okay, well, x is 1. If x is 1, then I got to move that 3 over, and the y would be 4, right? If x is 2, then I move the 6 over, and y would be 1. And what happens there is that because I left it in this implicit form, when I want to substitute x's in to find y's, I got to do that algebra subtracting that amount over every single time, right? And that's redundant, time-consuming, tedious, whatever you want to say. Same thing would happen here if I left this way. If I say, I'm going to say theta, let's say theta is pi, then I need to make this 3r times -1 plus 0 equals 7. Then I would have, what? R is equal to -7/3. And then if I make, theta go to, let's say 3 pi over 2, I'm going to have to run through the same algebra again, right? Okay. I don't want to do that. I want to set this up to where it's a little bit easier for me to evaluate. So the best thing to do then is to solve for R. Would you guys agree that both sides or both components here, both terms have R in it? So let's factor that out. We get that. And now we have the product, so we can divide by that factor of 3 cosine theta plus sine theta. And now we have our polar format. Okay, so what I want to show you here is a applet that shows I'm going to plug this in, and it's going to show me what that is as a rectangular system. Okay, so before I even show you that, what I'm going to do, I'm just going to go to a blank fresh start here, and I'm going to type in let's see here. All right, so what I've typed in here is that right there. Okay, that was what we just came up with on the right-hand side, correct, of our polar form. Okay, and you can see that curve. Okay, so what I'm going to open up now is this applet here, which allows me to do really the same thing. On the left-hand side, I'm going to type in 7 divided by, now it's 3 cosine. Instead of x, I'm using t here as my input, standing for theta, and then sine of t. So I get that, okay, which is exactly what we just showed, right? Okay. Now this side over here, don't worry about this side yet, okay? But what's happening here right now, you can see this green line right there, that green segment. Kind of hard to see from your seats, I get that, but right now that would be at an angle of 0 in a radius of something just a smidge over 2, right? Well, look what it does over here. It graphs that, okay, and it says, okay, if I have a theta of 0, so right here the solid green line is showing me the angle of theta that's been revolved out, which is 0. And now out on that, we're going to go a radius that's a little bit bigger than 2 and plot a point. Does that make sense? Okay. The next thing I'm going to do, I'm going to take, and it's easier for me to go to the algebra and then just type this in. So let's say I want to go to an angle of 15 degrees. So that'd be pi over 12 radians. You can see right here, okay, on this curve, so this is the angle measurement, okay, at pi over 12. and it's going to pull off a y value of 2.22. So over here then, we make a angle of 15 degrees, okay, or pi over 12 radians, and then go out to the 2.22 circle, which would be that right there. Does that make sense? Okay, you see the one circle and then the second one and a little bit further. Okay. Then if I go to pi over 6, plot that. So we're taking this at pi over 6, okay, which is going to be, so that's the theta that I revolve out. You can see the green line is showing me that angle of revolution of pi over 6, and that's the angle of revolution from the standard or positive polar axis here. Rotate pi over 6 radians, and then capture the y value here of 2.26. So we go out to the first circle, second circle, 2.26 circle. Does that make sense? Okay. Now that, when I highlight that right there, that 1.13, 1.96, don't worry about that. That's not the ordered pair that is being plotted. I'm actually not certain what that is. That might be, yeah, I'm not certain what that, I have to look at what that's referring to. But the ordered pair that's being plotted is, for us, 30 degrees or pi over 6 and 2.26 as a radius and theta. And I keep doing that. So when I move this, what's happening is that we're capturing these thetas and plotting them against these y values, okay, over here. So what ends up happening is that we end up getting that red shape. What is that red shape? It's a line, isn't it? Now what happens, and you can kind of see, you know, I traced out of these, and then as this is rotating, so this is demonstrating the angle of rotation, and this here is the opposite ray for that angle of rotation, right? In case I ever had a negative radius. So here we're saying I have a negative radius of 4, so -4, so I would go out, what is that? It's about, it's a little bit bigger than 3 pi over 4. And that distance there is a little bit bigger than -4, so I'd go 1, 2, 3, 4, but then flip over to the negative side, right? Does that make sense? So that's why it's kind of building it that way. And then we get some repeats as well, because if I have a negative, let's just go see if I can get to a negative 7 pi over 6. Close enough. So if I go 7 pi over 6 here, 7 pi over 6, it's a negative, a little bit bigger than -2, so I go 7 pi over 6, and then I go, okay, -2 would be right there, and that's the exact same point that was at pi over 6, right? Okay, so you might get redundant points, is what I'm trying to argue here when you do this. But nonetheless, we've typed in this right here, okay, which is our polar form, and we can see how that then creates the curve over here. If I were to type in, I'm going to click on here, I'm going to type in 3x plus y equals 7, does it plot that line right on top of what we came up with the polar form? Does that make sense? Okay. So really what's happening here is just basically this program is using these relationships to pull out values to plot that came from x's and y's. Okay, it's redefining those based on theta and a radius now. Is that okay? So this one is very similar to what we did on Friday as well. Okay, this is a circle. Where's the circle centered at right here? Okay, so it's centered at 2, 0. What's the radius? Radius is 2. I just put that information down because I want to see when we're done, how does our answers, information, and the way it's presented, does any of that stuff show up, or any relationship that can be realized from the equation show up? What I think, and we did this on Friday, we know this is a circle, okay? And And we could do this, guys. We could do this with other formulas. We could do it with hyperbolas. We could do it with parabolas. We could do it with whatever we want. Just right now, as an introduction, it's easiest to do with circles and lines. But we have x is equal to r cosine theta again. Y is equal to r sine theta again. And I'm going to write r squared is equal to x squared plus y squared. I know that I probably need to use that substitution, because right here I'm seeing a y squared and eventually seeing an x squared, right? You can make the substitutions right now. You can go ahead and say, okay, I'm going to replace that x with r cosine theta. I'm going to replace that y with r sine theta. And then square things. It works. It's fine. I don't like doing it that way. I think it's more work. What I like to do is just expand this first. Okay, because I know I want to use this, so let's get an x squared plus y squared to be present. So when I expand this, I get x squared minus 4x plus 4 plus y squared equals 4, right? You guys agree with that? Okay. Now, in the examples that we've seen so far, the 4's cancel out. That's not always going to be the case. That just happens. So now I get x squared. I'm going to reorder this as y squared minus 4x equals 0. What can I do with that thing now? Replace it with r squared. What can I replace that x with? R cosine. Okay. Now, just when we do polar equations, it's always r. Okay. It's never going to be r squared because it's referring to the radius, right? Okay. So we want the radius to the first degree. So what we're going to do here is factor out an r. So now we got the zero product property. So we get r is equal to 0. And r minus 4 cosine equals 0. So I'm just going to go ahead and solve that for r. It gives me 4 cosine theta. Let's just look real quick, and I'll use the applet I just had up to demonstrate this. If this was 0, okay, now we're plotting basically the theta against the distance that that point is away from the x-axis here. And that was the line we had in from the previous question. So does that graph anything? It might be graphing the pole. Does that make sense? But it graphs the pole over and over and over and over and over and over again, which is just the pole. So that's a pretty boring graph, right? So that r equals 0 is something that we ignore. Okay, we're not going to, that's not what we're looking for. That's not this circle. Okay. But if we have 4 cosine theta, okay, now this is where, and this is kind of the introduction that helps us understand maybe the next section. If we have theta, so basically what we're going to do is we're going to run through theta being 0. Let it be pi over 6. Let it be pi over 4. Let it be pi over 3. Let it be pi over 2. And we go all the way up to 2 pi. And plug in here, just like we would if it was in x's and y's, right? We plug in there, and it's going to spit back all of the r values. Then we would plot those just like we've always plotted polar coordinates. We trace out the theta and then go that many circles out and plot a point. If we did that over and over and over again for 4 cosine of theta, okay, which we know 4 cosine of theta looks like this, right? It's cosine. This is the cosine function. It's been stretched by a factor of 4. Now what we're going to do is we're going to go insert theta and capture the r that gets out of that, right? Does that make sense? And when we do that, we plot those points. Doing that on the right-hand side, so evaluating at certain thetas, evaluating this at a theta to get an r back. Okay, remember r of t. So r is going to be the radius at that input of theta. When we graph those, on the right-hand side, we're demonstrating that we get a circle, right? Okay, and what happens here is that because of how we graph negative values on these negative radiuses on a polar coordinate, we see that really we get, once we go through 0 to pi, that'd be 3.14, right? 0 to pi, we get our entire circle. And then going through again, we just get repeats. Okay? But that circle, now let's look at that circle. Where's that circle centered at? 2, 0. What's the radius of it? 2. Is that the same information that we had when we looked at it up here? Yeah. Okay. Now let's look at this here real quick. So how can I get that? How can I realize that from just R for cosine theta? What happens is if that function there is cosine, it's going to be centered on the x-axis. Okay, so whenever this is cosine, the circle is going to be on the x-axis. The radius is going to actually be half of that number right there. And the center, because it's on the x-axis, that's cosine, the center is going to be half of that as well. So 2 would be the x value of the center. Okay, so there is some relationship between seeing that and identifying what the actual radius of the circle is and what the center of the circle is. So I'll just demonstrate that a couple different times. So this one here, if I put 4 cosine in, there's that one we just did. Okay, now let's put 6 cosine in, and let's see where the center goes. The center goes to 3, right? Okay. I put 7 there. The center should go to 3.5, right? And it does. Okay. And you see that because it's cosine, it's always on the x-axis, correct? Well, what if I want to get over here? What do you think I could do to flip it over here? Yep. Put a negative out in front. It does that. Okay. What if I put a negative on theta? What does that do? Does nothing, right? And the idea is that because if I go negative theta, if I go, and I'm going all the way from 0 to maybe negative 2 pi, am I traveling through the same angle measurements that I would if I went with 0 to 2 pi? Yeah, okay. It's just in a different order, so it's still going to produce the same image. What do you think is going to happen if I make this, instead of the cosine, maybe I make that sine now? Yep, so I'm going to put it on the y-axis. And because it's now negative, it's going to be down here. If I want it up top, very positive. Okay. See how we can move it now to different positions. And we'll talk about that maybe tomorrow. I don't have any examples of that right now, how I'd go from maybe this, see what maybe the rectangular version of that would be. Maybe we'll do that tomorrow. But we can move. It doesn't always have to be similar. The ones that we see in this class for the most part are going to be centered on one of the axes. But it doesn't have to be. It can be anywhere in the Cartesian plane. Okay, or polar plane. Is it okay with that? All right, so here's the thing. The structure of these, structure of the one we did on Friday, same as the structure we did today, the processes are the same, right? It shouldn't matter what our -2 and our 4 are here. We should be able to do the exact same thing every single time. Okay. And if it was centered at like 2.5, basically what would happen is I would expand that. I would expand the y minus 5 squared. I would still have an x squared plus y squared somewhere that could be replaced with r squared, but then I would have a 4, maybe a negative 4x, and maybe like a 5y or something like that. And then I have to make that substitution of y as well. It's not that difficult. Yes. From this part here, because every circle is of the form, and rectangular form is x equals h, or x minus h squared plus y minus k squared is equal to r squared. And it has to do with transformations. Now, usually transformations we think opposite. So if it's how can I phrase this? Like if I had, so with transformations we have like y equals like x minus like 5 squared. You know that's going to move right 5, correct? Because this is implicit, the x's and y's are on the same side, the same approach and the same logic that we had here for moving to the right 5 is also going to be true for the x and the y. So the center then is always located at h comma k. So if this was like x minus 2, it'd be to the right 2 instead of left 2. If this was y minus like 5, it'd be up 5 instead of down 5. Does that make sense? Square root. In rectangular form, it's the square root. So down here, we're going to go in reverse order. Okay, and there's a handful of these that we're going to do. We're not going to do all. I think there's like 8 examples here. We'll maybe do 4 of them. And this first one's pretty easy. R equals 8. What am I telling you when R equals 8? What's R stand for? Radius. Radius is equal to 8. Radius equals 8. Do I tell you what theta needs to be or any way to develop theta? No. So what's that telling me about theta? Theta is going to oscillate between 0 and 2 pi. It can be anything. It'd be like me saying, let's do this. Let's say x equals 5. Rectangular form. What am I telling you y has to be? Y can be anything. I'm telling you what x needs to be 5. But then the y values can be anything that they want to be, right? So same thing here. R has to be 8. And thetas can be anything. And if I pair a bunch of thetas up, okay, no matter what theta I want. Okay, so let's go to this one here. Okay. And we just have, oh, not that. How can I do this? Basically what I'm saying is, as I rotate this number right here is my theta, right? If I rotate that through, don't worry about this point being plotted here, but if I rotate that through and I pair 0 with 8, and then I pair pi over 6 with 8, and I pair pi over 3 with 8, be up here, and I pair pi over 2 with 8, and I pair 2 pi over 3 with 8, and I do that all the way around, what am I going to get? Yeah, so if I go 0, 8. Well, let's do it, because I've got some things messed up there in the way I formatted that. Let's go here. If we go 0, 8, Not sure why that's doing that way. The logic, though, okay, is now if I have all these ordered pairs and I want to graph them, 0, 8 would be there, okay? Pi over 6, I would go out to pi over 6 radian and plot on the 8th circle. And I keep doing that, and all the way around, I'm going to create a circle, right? Okay. Now, what would that circle's radius be? Circle's radius would be 8. Okay. What would its center be? 0, 0. Okay. And like Keaton just said, or just asked about, that x minus h squared plus y minus k squared, where h and k is the center, that would give me x squared plus y squared, wouldn't it? Equals r squared. R was 8, so it gives me 64, right? Okay. Let's talk about how we can get from that to that algebraically. We just did it kind of logically, okay? But don't we know that r is equal to the square root of x squared plus y squared? So then if I go x squared plus y squared underneath the root is equal to 8, square both sides, do we end up getting exactly that? Okay, so I think that's the easier one, okay? But going through that imaging, I think helps understand maybe why. So here's the idea why I think this might be a useful thing. And I could be, I might be oversimplifying things, but when we talk about applications of this stuff, and that's what I think is important for us to understand, is that there is a purpose somewhere for these polar coordinates, okay? And I would argue that maybe it comes into use when we are doing programming of robotics, okay? Would you guys agree that kind of right there, so look at the right-hand side here when I zoom in, that there is that arm is going to have to rotate many different spots. Okay, you see my hand right here on the left-hand side with the yellow box? It's kind of hard. I like this picture because it's kind of the best one. Let me do it this way. That's better. Kind of. All right, so right here, this portion is going to rotate towards you and away from you. Does that make sense? And it's pivoting right here on this circle. Okay. In order to do that, it needs to be programmed to do that, right? Okay. This here, okay, this circle here, it's going to rotate around there. You can see right here at this joint there, it can rotate this direction. Does that make sense? Okay. Same thing's happening here at this kind of juncture or joint. It's going to articulate down and back. And then you got the same thing here. There's a lot of different places that this thing is going to be able to move, right? Okay. The programming of that, for that to move in a circular motion, maybe, I'm not going to say it is, because I don't know that degree of programming and all that kind of stuff, but it may be easier to program using this equation here versus that equation there. Does that make sense? How many inputs do I need here for this one? Yeah. Okay. How many do I need here? Yeah. Okay. So that's the idea that this is more simplistic, and that's what we're going to find out. And we're just scratching like the surface of the surface. So when you get to, I never used this stuff in college and undergrad work. It wasn't until I say that, but it was 4 years of schooling that I might have missed. I didn't miss any classes, but I might not have been fully paying attention. But I don't recall this being a huge topic of discussion in undergrad work. Okay. Now, if you go into engineering, maybe it will be. Okay. You go to mechanical engineering, probably will be. Okay. But I didn't see this stuff and really work with this stuff until I got to a class called complex analysis in college, which is working with the complex plane. graphing something like 2 plus 3i. And then using that in connection that allows us to do some of our algebra that we're used to, maybe a little bit more efficiently. But day one of that class, like the first 4 homework problems, were devoted to this, okay? And then the rest of the course was kind of built off of it. Does that make sense? So this is a topic. It's called, like I said, it's called complex analysis. That you would spend a lot of time transferring between rectangular equations to polar equations and vice versa. And what we find out in that class is that the algebra in rectangular can be very monotonous. For instance, and you're going to see this in a couple days. If I ask you to take 3 plus 4i and square it, you have to go 3 plus 4i times 3 plus 4i. You have to FOIL that. You have to see that I squared is a -1 and then combine like terms and all that kind of stuff, right? And that's not too bad, but what if I make this to the 200th? That's a pain in the butt, right? You're not going to be able to do that within the time frames that you have, okay? And if you do, you're going to probably make an error somewhere, okay? What polar coordinates allow me to do is to find that exact same answer within seconds, okay? So we'll do that eventually, okay? And that's what that complex analysis class is. It demonstrates, okay, yes, we know how to do this stuff algebraically through 2 variables, but how can we do it in the polar system to make things more efficient? What's going to be the equation here of r equals 4? X squared plus y squared equals 16. So they're telling me r is 4, radius is 4. And then there's that knowledge that it's got to be a circle. All right, these ones I think are harder. I think these are the hardest ones we've done so far, because it's not, especially this first one, it's not a direct or as direct substitution-wise, procedural-wise as the others have been. Okay. All of these use 2 trig functions, cosine and sine, right? We are presented now with secant. That, to me, is a big problem. Okay. I also see this because it would be nice if it was like -2r secant, because I don't have any r's on this side, right? So there's not like a direct capture of this thing over here and substitute it. Can't do that right here. Okay. Not until we do a little bit of manipulation first. Can I rewrite this way? You guys agree with that? Okay. Now I'm going to ask an open-ended question. What are you allowed to do to an equation? I can multiply both sides by anything I want to, right? So you can do, so that open-ended question is, what can I do to an equation? Answer to that, anything you want, as long as you do it to both sides, right? So, cosine theta. Multiply by cosine theta. Cosines cancel right there, right? What am I left with on the right-hand side? R cosine theta, which is x. What am I left with on the right-hand side? -2. X equals -2. Okay. X equals -2. Now, I would probably argue here, and that's a lot easier of an equation to deal with than what that one was. Okay. Yeah. Yes. Right here. Right. If I get rid of that negative, then this is going to be positive 2 down here. Let's take a look. So we go 2 secant theta. So you see how it's, because it starts me between 0 and 360. So it starts me at so if I get, I don't want you to say that there's no negatives, because if I put a negative here, instead of plotting that point, it's going to plot this one here. Does that make sense? Instead of plotting this point here, it'll jump over here and plot this point down here. So it's going to create a vertical line here instead of a vertical line there. Does that make sense? So you do need that negative, and now you can see that it jumps across. It's going to plot those across. Good question. Let's do one more real quick. Time we get out of here. Yeah, we're not going to get this one done. We'll start here tomorrow.